Now remember that for sequences, we said that, well, sequence is convergent if the limit of the sequence exists, and it is divergent if it doesn't exist. Well, something like this happens for series as well. Of course, the series is in fact a sequence, and so we're going to say that a series is convergent if the sequence of partial sums is convergent. Now notice I'm using Sn now, not Sk. Remember that letter that I use at the bottom doesn't really matter which letter it is, as long as we're clear on the fact that we're dealing with a sequence of partial sums. And just like before, a series is going to be divergent if in fact the sequence Sn is going to be divergent, which means either it may go to infinity or may be oscillating and not go to anywhere in particular. All right, so now remember that for sequences we saw only one theorem, one fact that related to the convergence of sequences, namely that a sequence that is bounded and eventually monotonic is going to be convergent. That's the only fact that we saw there. Well, for series we're going to have a whole bunch of theorems and ways of checking if a series is in fact convergent or not, because of course series are way more interesting, more important, more applicable than just general sequences. The first one we're going to see, however, is fairly basic, and it's a divergence theorem, not a convergence. It's something that tells us which series or whether a series that we're dealing with is divergent. Okay, and again, it's a very basic fact. We're going to be using it over and over again. It's going to come up all kinds of times. So let's make sure that you understand how it works. So the idea is the following. Let's say that a series converges. Okay. Well, if it does, then the sequence from which it comes, remember each series comes from a sequence of terms which we're adding up, well, that sequence of terms has to converge to 0. Why is that? Well, let's assume that Sn converges, right? And let's assume that its limit is some number L. Okay. Now, obviously, I can write the number 0 as L minus L. Remember, L is the limit of the sequence of partial sums. So I can write L as the limit as n goes to infinity of Sn, or I can write L as the limit as n goes to infinity of Sn minus 1. I'm going to the same limit, I'm just doing it one step behind. But both of those limits are going to be going to L. Now, if I take the difference between those two limits, the difference of the limits is the limit of difference if both limits exist, and in this case we're assuming that they do exist, well then the limit as n goes to infinity of Sn minus Sn minus 1 has to be equal to 0. Remember, we started from 0. But how much is the difference between Sn and Sn minus 1? Remember, that's the sum of all elements up to n minus the sum of all elements up to n minus 1. What do we end up with? Well, just the nth term of the sequence. And so that means is that the limit as n goes to infinity of the sequence an has to be equal to 0. Now you might say, why is this a divergence theorem? Well, it's a divergence theorem if we read it the other way around, which is the way that we're going to use it in general. Because, remember, what we're looking for is whether a series is convergent or not. The statement I just gave you assumes that the series is convergent. But let's read it backwards. What this same statement says is that if the sequence of terms an does not converge to 0, then obviously Sn cannot converge, and therefore it has to diverge, right? This is the contrapositive of the previous statement. Okay.